So thank you for the introduction and good morning everyone. I'm Akhil Francis. I'm a postdoc from Berkeley Lab and today I'm going to talk about excited state preparation in quantum computers. So we know that like excited states, studying them is important. They are the different eigen energy states of your system. And then these are relevant for like various applications. Let's say, for example, for interaction with respect to light or like photon sources. So studying them is important, and there are like various methods to prepare, these excited states, both in classical computing as well as in quantum computation. And we are looking at these variance-based methods in our approach. So the idea is this, that this is the cos function that you have, which involves like Hamiltonian as well as the square of the term, and minimizing them guarantees that it goes to an eigenstate. So meaning that if variance is 0, it's guaranteed that it's an eigenstate. And there is also an associated method called this folded spectrum, which allows you to like specifically target a state. So if you know the reference energy or omega that you a priori know, then you can feed into your cos function, and by optimizing this cos function, then you can go to a more targeted state. So typically this is done in quantum computers in a hybrid fashion. So you have an appropriate ansatz. For example, you can consider unitary coupled cluster ansatz, like talked in the previous talk. And once you have that ansatz, you measure different terms in your h square. Then you make that cos function in your classical computer and use an appropriate optimizer to do this iteratively. And this has been studied, in the quantum computing setting in various of these studies. And like we are actually interested in applying this for like quantum chemistry molecules. So let's look at how does this perform for like a hydrogen system. So I have the Hamiltonian that I can write down, and I can excitedly diagonalize and put various of my energy levels here. That's on the left column that you see. And in particularly, I'm interested in 4 of these 2 electron states which have marked as energies here. So the goal is to get these energies. And in order for that, we need appropriate state to start. So I consider this different bit string or Hartree-Fock states or single determinant states, however you call them. So those energies are given by this green. For example, ground state, you can see that really close to the actual value, but it still needs to be improved. Similarly for these other states. And one can construct now one needs an appropriate ansatz. So I consider the UCCST ansatz, which is made of single excitation and a double excitation, like we talked in the previous talk. And then using that, I minimize the cos function various, and I can see that, for example, this state improves to this one improves to this. There are 2 states degenerate here, so they both goes to here. So this actually guarantees that, you get all the eigenstates, but we would like to get more targeted states as well. So I could also provide the exact energies into these reference states, into this cos function, and I can also get using folded spectra too, as marked by these red labels. I can get the energies in that way too. And it's the feature that I can target energies more like this, which variance was not able to provide. It's an attractive feature of the folded spectrum method. So I'm going to talk more about folded spectrum from now on. So earlier I looked at one particular bond length of the Hamiltonian, I looked at a hydrogen molecule near equilibrium, and now I basically want to reproduce this for across different bond lengths. So on the x-axis I'm varying my bond length. And for example, now look at, let's say the energy plot. And earlier I showed all the 4 eigenstates together, but now let's look at only the ground state. And the solid line represents, the exact energy that you would expect. And the blue and the green one is the starting energy, the Hartree-Fock or the bit string energy. And from there, I minimize my folded spectrum, this cos function, by providing exactly the energy, and then it goes to, the targeted excited state as we expect. And we can see that the change in energy with respect to the exact energy is also really small, and the variance is also really small, and it goes to 0. So in this way, we prepare excited states across throughout the different bond lengths for ground state. And I can repeat this starting with different single determinant states, and then target all the eigenspectra. And then we'll clearly have a really low variance, and the energy is also similar. Okay, so this is good, but like in the previous thing, I actually provided the exact energy, which we don't often have. So one would like to see that, even if I provide an omega or like a reference energy a little bit different than the exact one, which is often the realistic situation, we should be able to target those. And luckily, the good thing is that we actually see that in this method. So on the x-axis, I am varying my reference energy omega in the cost function, and I do the optimization, I get the final energy, and that's what I'm plotting in the y-axis, the final energy in the y-axis, and the different solid ones corresponds to all of those points. And these blue lines in the back show all the different eigenstates, eigenenergies, and I can see that like my initial energy is very close to the actual one. That's the Hartree-Fock state that I start from, and then I optimize, and then I know excited layer is the excited state here. But even if I provide an omega to the left or to the right, it will still find the targeted state, which is good. I mean, after a point, then it will lose track of that. But having this much of this kind of robustness available in the omega is a good feature of this method. Okay, so now I've demonstrated for hydrogen molecule, but now I look at a lithium hydride molecule and then a particular active subspace, and then only part of the spectra. And then again, I see that like starting from Hartree-Fock states, minimizing folder spectra, I can get this energy spectra. And similarly, I can provide this sensitivity curves here. Okay, so far, I've talked about measuring, implementing this with respect to like exact calculations, or let's say state vector simulations. But now in a chemistry Hamiltonian, typically one has a large number of terms to measure. So your Hamiltonian has, let's say, order of n to the power 4 Hamiltonian, n to the power 4 terms, right? And then squaring them would be like n to the power 8. So that's actually a lot of terms to measure. But one could try like, let's say, various grouping schemes or like various shadow tomography techniques and to address for this measurement reduction. But here, actually, what we do is we use a particular grouping scheme to analyze our system, and then we want to look at how this behaves, in the case of finite shorts. So I collect all the terms in the h and h squared together, use a qubit-wise commuting scheme, and then measure those representative polystrings, and then compute the cost function. So let's look at, for example, what happens, when I use variant, when I'm looking at the variance as a cost function. So this top left plot, let's focus on there. And the x-axis I have the number of shorts. So for example, let's say I have 100 shorts here, 1,000 shorts here, and one dot here represents that after I do the optimization, in this case using variance as the cost function, I minimize the variance and I go to an excited state, right? And what's the final energy corresponding to? That's one blue dot, and I can basically repeat this, let's say 10 times to collect some statistics, as you can see vertically here. So, and the blue dotted line here represents the initial energy, and the red dotted line represents the final the exact energy that we are interested in. So as I'm increasing the number of shorts, it goes from the initial energy to the final expected energy with more and more accurately, and with less spread in the statistics. So this is good. And one can also see what happens to the variance is exactly the cost function that I minimized, that variance also goes to 0. And if similarly one can analyze the folded spectrum method as well. So basically by minimizing this cost function, I get similar statistics, and I can see that with increasing the number of shorts, one could go to the expected eigenstate. Okay, so in summary, I would like to say that what we have tried is, what we have implemented here is X-ray state preparation using variance or folded spectrum method. And the nice feature is that this is a self-verifying cost function, in the sense that it's guaranteed to be an eigenstate if the variance goes to 0. And the folded spectrum allows for more targeted preparation of your state. And then we have looked at this using UCCSD ansatz. For the chemistry systems, we have looked at hydrogen molecule, lithium molecule, and then we also see that how much sensitivity is available in the reference energy, and we have also looked at what happens in case of finite shorts for the smaller systems. And yeah, thank you for your attention, and I'm happy to take any questions if you have.